We talked about the hierarchical prediction system that somehow mimics the cellular path. We talked about having a system that is robust against sequencing errors, that gives one framework for the domain of life, that somehow uses signals of conservation, motifs to predict, so it puts evolutionary information into the system, has membrane prediction, and has the reliability score and has high performance. The answer to all of that was Loctree, and I showed you the sort of first step that you do in order to assess a method, where you simply do a k-fold cross-validation, stratified cross-validation, in which you essentially establish the hyperparameter solution. So you establish that this is the best method, and the next step is establish that this method performs at a certain level. At this certain level performance, the first kind of data that you present is the confusion matrix, where you have a set predicted in the subset localization, set of proteins predicted correctly in the set localization L, predicted correctly not to be in L. So these are the sum over the diagonal. Here's the correct predictions. That is often referred to as the confusion matrix, in which you simply have the numbers. And then, in fact, you fill in false positives, false negatives. You use these numbers to sort of calculate all kinds of levels. But first, if you see these numbers like this, is that good or not? And you may sort of come up to an answer, but it is much better to sort of convert them into percentages. And there are two ways of doing the percentages. So the simplest, or there's a variety of ways of doing the percentages. The simplest one is you simply do a percentage of the diagonal, often referred to as accuracy. I refer to it in a two-state prediction as Q2. Then there is the sum over true positives, false negatives, divided by true positives, and then there's sort of the sum over true negatives, false positive, and true negatives. That's sort of this sum, then you can sum in that direction here, and all of these are essentially called something else. This is typically referred to as precision and recall. Precision simply says, if you predict a set of nuclear proteins, how many of your predictions are right? That's precision. If, however, you ask how many of the nuclear proteins that have been observed do you actually predict at that level, that's recall. And that completely ignores the negatives. Unfortunately, there is a set of very different words. These numbers are completely symmetric. You see that all you do is replace the TP by TN, so the positives by negatives, and you get a completely symmetric value. This is no longer called precision, which I find is a mistake. So historically, I've avoided these words. There's another way of calling these here accuracy and these here coverage, and then this is accuracy of positives and negatives, and coverage of positives and negatives, and you see that they're completely symmetric. Although I understand this is complicated for many publications, but you really need, in terms of assessment, you really need on the one level all of these sort of confusion matrix related issues, precision, recall, and others. Then you need something that is related to the ROC curve and AUC, so that sort of assesses how your tool performs throughout and allows others to compare to you based on precision and recall. And you need something that sort of gives the user the possibility to see how the threshold relates to a certain expectation in performance. Precision, recall, possibly in F1 that sort of averages over these two. But now we get back to this issue we discussed already, are more digits better than fewer, and that gets us to this definition of a standard error. The standard error defines how many digits are important. If the standard error were to be plus minus 0.8, then essentially, most likely the right way would be here to remove even the digit, essentially only the integer would survive. Once you have two methods that you compare, you need to look up where is random, where is the top, the experimental error, and say in the spectrum in between, you can then sort of reassess the question, are these two in fact different, are these good, are these bad? Now, in terms of are these good, are these bad, this brings us back to the question, which method is best? Assuming here that the standard error is 0.8. So, is this method the best? Is the question. Well, numerically it's clearly the highest value, but it is the best. Is that enough for you to claim in your publication, I have the best method? No, Kira says correctly. So they do not differ in a way that is statistically significant. That means you cannot, from that result alone, maybe you can find something else. Maybe you can see that your method does something that is its scientific value that the other method has not. It can predict secreted proteins better, or it can do something else. But that you have to prove. Or is as an input to some other method that uses it, allows something that this one cannot do. But just based on these numbers, if the standard error would be 0.8, cannot claim that mu3 is better than n1. That gets us to the next issue. Say the standard error were 0.8. I have these 5 methods here, and I would ask you to please sort them. So you do a bootstrap, and that brings us to how well does the method work. How well does the method work? Well, again, we have this hierarchy where we go into the path of non-membrane and membrane, and then increasing level of detail. For instance, the first decision is soluble transmembrane. Now, that decision here for our method has 94%, and we compare it to sort of the best alternative or available specialist with this polyphobius. And polyphobius is better numerically, but again, you see in terms of standard error here, you cannot clearly distinguish between them. So we keep the entire system, and we are not replacing it by polyphobius up there. You see that down here, most of the decisions there are exceptions to this, but most of the decisions tend to be lower down here. And by the way, I reversed the tree. This is the membrane part now, so I switched the tree. In the previous version, the membrane was here. No, the membrane is here. Anyway, I just made a mistake in the way membrane is to the right. I just made a mistake in the way I said it. Anyway, you see in some cases here, the lower points have relatively high values, but for many of these, the lower points clearly have levels that are lower than the decision up there, which was 94%. Why is that the case? Why does it get more difficult when we get down there? Why is performance getting worse? There's a variety of reasons. Yes?
I mean, because your error multiplies.
That is one important issue. Whatever mistake you make up here, it will be added to whatever is made as a mistake on this level here. You cannot. So the final decision here is chloroplast versus mitochondria, right? If actually it was a secreted protein that a non-membrane protein that you lost somewhere here, there's just nothing you can do about this anymore. Okay, you cannot. This decision does not, unless you would sort of do SVMs that would. One way of doing that, and we have never done that, is that you at every single point have one that says this is the right path and everything else is the wrong path. But then the problem is you need 3 states, and with an SVM you cannot do that. So you need the other path and the wrong path. Anyway, maybe there's a solution of doing that. It's not trivial. Ultimately, that's one problem. Errors sum up. What else is the reason why the further down you go? Yeah.
Class size, maybe?
Absolutely important, absolutely crucial. So the further you go down, the more detailed decisions you make, the the fewer data points you have. And we could always, this is of course not against the negatives, you could put in all the negatives and take everything else that you used before, but in terms of machine learning, you will always need as a driver the smaller class, whatever that is, positives or negatives, and that smaller class is going to get smaller and smaller the smaller the class. There's just no way you can recover from that, and that is a crucial issue. And there's another issue. The other issue, best to illustrate that, is ultimately here Golgi versus ER. What happens here is that the decision is getting extremely difficult. So these things are proteins that are increasingly similar in the way they look. So they all have a single peptide. ER and Golgi, both of those have sort of C-terminal peptides or motifs as well. So there's a lot that they have in common. And the further down you go, the more complicated the decision gets. Even if you had enough data, it may be more complicated simply because these proteins look more alike. They pass so many other tests if you do it right? But then I said that the method was supposed to be resistant against sequencing mistakes. So I show 3 different methods here. The one that I'm talking about, full-length plotting. Essentially they are not that different in terms of performance. This is slightly better than the others. But then now you remove the 30 first residues and you see that yes, there's a drop, but for the other methods the drop is even more. Okay? And then you remove the last 30, you see the drop is less. It's also less for the other methods. And then you remove randomly and you see that is a high drop. In fact, for other methods this high drop is not as high. What you can sort of suspect from seeing this immediately is that this method here, and to some extent this method, but this one the most, uses some information contained explicitly in the 31st residues, such as the signal peptide. So this is something that you can already see. When we got this tool out, it looked like the best tool available at the time. Today we know it no longer is the case. The best tool available today is called DeepLock. It comes from a group at the DTH around Henrik Nielsen and Ole Winter. And it uses a deep learning architecture with a variety of things that sort of cuts out motifs, gets into recurrent LSTMs, goes into attention decoders, and then puts all of that on top of a hierarchy. And this hierarchy is very similar to what I showed you before, in principle. When you look at where is the information content the most, you see at the beginning of the protein, that is where it's darkest here. There are some compartments where the other region sort of has some information. And then there are sort of decisions such as cell membrane, where there's information throughout the sequence, cytoplasm, some of that, nucleus, also some of that. Back into terms of other methods that are available, all of these methods here use evolutionary information, and DeepLock clearly at the moment is sort of the best player. The project in our group tries to digest through transfer learning the meaning of a protein sequence. So ultimately the way it works is you learn from a protein sequence like you learn from sentences and then natural language processing methods, and you essentially learn to predict that given a set of 5 residues, amino acids, what is going to be the next amino acid. Okay? You train this on a large data set, essentially uniprot or some subset of uniprot. Incidentally, so we did this on UniRef 50, which is reduced at 50% sequence identity, meaning you take the entire uniprot, and you keep only the set of proteins that have less than 50% sequence identity to each other, every pair, right? That creates a data set of 35 million sequences, which in fact corresponds to something like 10 times the size of Wikipedia. So it's a large data set, completely, yeah?
I have a question to that. Always, like when you calculate the less than 50% sequence similarity to each other, well, how do you choose which one you keep in? Because depending on which one you keep in, your percentages to the other proteins will change. Do you choose those so that you keep the maximal amount of proteins?
So in the future, yes. And there are different strategies. So you can choose the longest one, you can choose the first one, you can choose the shortest one. And is that...
Or you start basically with a set and then you add...
That's what you do. But still, at that very position, still...
But it depends on which order you add the proteins, right? Because if you shoot...
Exactly, that is where the sorting becomes important. Do you sort by alphabet, do you sort by length, or do you reverse sort by length? So shortest first or longest first. And they give different solutions, and they are relevant for different problems. And there is no one answer. The default is most likely what has the least assumptions, which is alphabetical sorting, which is nonsense. But again, so the other two extremes produce a lot of nonsense effect for in some instances too. And they both have big disadvantages. Anyway, so you essentially train a machine to learn unannotated simply sequences, okay? Once, just like Google learns sentences. This is what you have on your cell phone, on your watch. These are sort of text correcting software, and this is what this one too does. And then you put whatever that learns, the embeddings, into some other machinery, right? For subcellular localization, that's where that ends. So then you put another machine learning on top, which is a simple deep learning device without any further optimization, that does not, like Loctree, uses motifs, so that just uses essentially these embeddings in a very simple way. And you see that the performance is less than the top of the line, but the performance actually is almost as good or numerically similar to whatever is the second best using evolutionary information, while this device absolutely doesn't use evolutionary information at all. So the challenge is now to put evolutionary information into this thing in a clever way, such as the motifs that I was talking about. Incidentally, so what this tool does is essentially learns protein sequences, but in a context-specific way. So when you learn protein sequences, you always know what is before you. There is another way sort of to extract embeddings from a tool called ProtVec that essentially classifies proteins and extracts embeddings, but in a context-in-specific way. So essentially, he learns what's the probability of an A, not the environment of the A. Okay, and you see this is much less successful. Again, this is all put into some deep learning device as input in the same way. It's just that the embeddings are different, and the embeddings are created by the device in both cases that has never heard about subcellular localization. It's just a feature extraction procedure, if you want. Anyway, now the other issue with Loctree is we have a device that predicts for proteins for which you do not have any homology information, but now we want to sort of put the homology information back into the fold. So we want to put it up as a server. Putting it up as a server, historically the way we did it is we said, okay, we have a prediction method. The prediction method is less accurate than if you look it up by homology-based inference. So if you find a protein of known subcellular localization in the database, so if you have the similarity, sequence similarity between a query and a protein experimentally characterized that is larger than some theta, then the best way, that's homology-based inference, HBI, then the best way would be to simply look up the experimental value for E and use that to annotate Q. The problem is you have to point to a database, you have to trust that the user will follow that link and has the time to follow that link there, so there's all kinds of assumptions. And that's why we decided, well, actually we should sort of merge the two. The prediction device and the homology-based inference, and give the user one answer, and the answer also give a source. So we are saying that this protein is nuclear because it's HBI. So it's homology-based inference, 2, and here's E. Okay? Or we say this is a de novo prediction, and here is the system. Okay? How would you combine them? But what you said, essentially, Konstantin, is the idea of picking whatever has the highest confidence. Because they both come with confidence scores, and you simply could take whatever is the highest for the individual prediction. And we would have to test whether it does better. What we did in the end is we picked one threshold, 10 minus 3, is you simply could ask, how, if I predicted subcellular localization, one advantage of subcellular localization over prediction of subcellular localization over experimental values is it's available for every single protein, right? So I could simply apply it to entire organisms. And then I get sort of these pie charts. And you see some things that are surprising. For me, very surprising was how high nuclei is for all of these. You see some things that are surprising on a level that you cannot quite explain, and I will sort of resolve that. There is an issue here, which is this nucleus is more similar to the nucleus of a chicken than it is to the nucleus of an orangutan. Now, we don't like to be more similar to a chicken than to an orangutan, most of us at least. So, okay, this is because the guy who was sequenced here had chicken. Now, anyway,
What?
Ate too much chicken. But so you see all kinds of interesting things. What I don't have, what you have to look at then is, well, you could argue we make mistakes in the prediction here. So wouldn't it be better if I looked at a subset of all the proteins in that organism for which I have experimental values? And so the slide that I skipped here is one where the inside circle has the experimental data, and just to summarize it, essentially, the experimental data gives some predictions that are total nonsense. So it's clearly wrong to use the experimental data. It's clearly better to use the predicted data. But there's an additional step that we have to do. And that additional step has to do with this question. So with roughly 20,000 proteins in human, say we had a method that predicts membrane versus non-membrane. I'd say that method predicted that 5,000 human proteins are predicted to be transmembrane and 15,000 are predicted to be not transmembrane. My question to you, what is the transmembrane fraction? Well, you may argue 25% obviously, right? And that comes up with the question, can you not do better? What's wrong with the 25% number? Yeah? Well, there's no error estimate. That's not what I'm talking about. I mean, yes, it's what I'm talking about, but I'm not talking about standard error, yes?
Are we assuming that we know all human proteins?
Yes.
That we found all?
Yes. So whenever you make a statement, let's not call it all human proteins, let's call it all proteins in the subset that I have. And still the same problem arises. The problem is the following. Consider we had an error of 10%. Okay? So this 10% error would be, of the 5,000 predicted to be transmembrane, I would have to subtract 500. 10% are wrong, right? 500 are wrong. I don't know which ones, but I know on average 5% are wrong. Of the 15,000, I would subtract 1,500. And then I would take these 1,500, put it on top of that set, and these 500 put it on top of that set. What I would end up with is 6,000 predicted to be transmembrane and 14,000 to be non-transmembrane. I do not know which ones anymore, right? But I do know that the numbers should be like that, simply from the fact that I have 10% error. And you immediately see that, and now we get into a slide, oh, that is still the right slide. So you immediately see that this is now 30%, right? So essentially all you need to do is, this doesn't help here, all you need to do is sort of change the confusion matrix, or use the confusion matrix to change the expected distributions. Essentially do the correction just the same way I did it manually here. Except for in real life, the story will be slightly different because the 10% will not be the same for this and that. Yes?
This only works with binary classification.
No, it does not work with binary classifications only. Here is essentially the completely general.
But I mean, if I knew that, okay, 10%.
Yes, so the problem is not 10.
Well, you don't know into which of the other categories to shift it to.
Yes, you know exactly from the confusion matrix, you know exactly in which category to shift. That's exactly what is in the confusion matrix. Yes, you do know. Precisely, in the confusion matrix you have whatever goes wherever. So you know what is predicted as, and you know what is observed as. You know the class it is predicted in, and so for every single class you know where from which other class the mistakes come. And that's exactly how you can sort that out. So mathematically it's a very simple correction. This is the way the correction looks. It comes from the substitution matrix. What I show here is estimating for some data set the overall composition without, so just looking at the 25% kind of idea, so just taking as head on, and here using the confusion matrix. We have two methods here that have a fairly different performance, but the error estimate for the entire distribution is very, very similar, yes?
Then all methods that you have should give you the same final distribution, right?
Not quite.
Theory.
Not quite. So that again, that depends. So if you're totally wrong, then you cannot correct for that. Right? Let's just look at the most extreme examples. If you're completely wrong, no way to get out of it.
What do you mean by completely wrong?
So if you had a random prediction, you cannot recover from a random prediction. because the random prediction would reshuffle in a random way, and you would still get a random prediction.
But if you know for each of your methods what percent of were correct predicted wrong, and in which category the wrong prediction would fall.
But in a random, it would be random.
Right. Okay. Well, yeah.
And there's no way out of the dilemma, okay? So, but you see that ultimately the degree to which this is more alike than this is exactly what you say. Right? You move toward more alikeness. So you get something that is first of all more yellow. So these are more yellow than these for all. So these are more right, these are values are, so the difference between observed and predicted, so to speak, is much less on this side than on that side. And they are more similar to each other than these here. So error correction helps. Now you can then use the error correction to sort of, and that's what was in the pi before, and this, by the way, work from Valérie Marot. And you can sort of redo the pi and show it this way. And unfortunately, I don't have the color coding here. The highest must be nuclear. It's most likely nuclear and cytoplasmic here. And then you sort of can use that and build a tree. And interestingly enough, for the species shown here, now we switched the orangutan to a chimp, not because we didn't want the orangutan because it gave a wrong result, simply because of availability of data. And you see somehow this tree makes sense if you do it into 2D rather than 1D. So in the first eigenvector, second eigenvector, or PCA, principal component, you see that sort of the yeast species are completely here. And here you nicely see the fly, the worm, the apes, mouse and rat, the mammals. So this is just using sequences of the organisms and the prediction method. It's remarkable what you can get out of it.